A warm greeting to the one at the other end. I'm super excited to share our solution for problem statement which comes under the Ministry of Jai Shakti, and our problem statement code is SIH1293, and our project title is Optimizing Irrigation with AI Soil Moisture Based Wall Regulation, and our problem statement title is Automatic regulation of walls for the release of water based upon the soil moisture availability in the root zone of the crop, and using AI in a piped and micro irrigation network of irrigation system. And we are from the team Agri Techies, and Devaraj, who is our team leader, and myself Monisha S, who is a team member, and we are from RMK College of Engineering and Technology, and our team name is Agriculture, Food Tech and Rural Development. And I am briefly explaining about our idea solution. First, sensor deployment, that is, we are going to place sensors, particularly here soil moisture sensors. Here we are using time domain reflectometry sensor to measure the soil moisture level, and this sensor is placed in the root zones of the crop, and it can be placed in the various levels of the plant, that is in level deep root zone level and middle root zone level and in the shallow root zone level, and these sensors provide real-time data on the soil moisture levels continuously. Then along with TDR sensors, we also deploy DHT sensor, which is digital temperature and humidity sensor, for the measure of weather conditions and to focus the weathers and to know about the temperature. And the data collection part, that is the data which are continuously monitored by these sensors are collected, and these are given as an input to our AI system. And we are also placing the camera modules in the field, and these camera modules are helpful in identifying the images. These camera modules will capture the images. By using these images, we can identify the factors which are also affecting the valve regulation, that is flow of water. Here the factors such as, the first one is plant type, the soil type, and also the plant growth stage, that is it can be in vegetation stage or in the fully growth stage, like that. And this data collection part then followed by AI algorithm development. The data which are collected are given as an input to our AI system, and here in AI system there is an AI algorithm that uses both deep learning as well as machine learning. Here deep learning comes into picture because of we have to find the plant type, soil type, and as well as the plant growth stage by using the image captured by the camera. These are serves as the input for our deep learning algorithm, and our deep learning algorithm will determine the respectively type of plant, growth stage and soil type, and then comes under machine learning algorithm, that is these data collected from sensors as well as by the data from the deep learning algorithm are given as the input to the machine learning algorithm. This machine learning algorithm will analyze and compare this real-time data with the field capacity. Field capacity is a concept that is particularly novelty in our solution. This field capacity is a default for some type of plants in some type of soils. For example, for paddy plant, for in alluvial soil, this should be the field capacity for the plant for optimal yield growth, so that the collected data from our model will be compared with this field capacity data set. By predicting the output, that is whether we have to open the valve or close the valve, this machine learning algorithm will determine the optimal irrigation schedule. And then data analysis and learning, and that is our AI system part, that includes deep learning algorithm, machine learning algorithm, and that AI algorithm development. And data analysis and learning, the data analysis learning is nothing but we are providing both machine learning and deep learning concepts here for continuously analyze the data collected by the system, AI system, to improve our AI algorithm. And our machine learning technique should be more adaptive and accurate for the various environmental conditions. And then finally valve control system. by the output of the machine learning part will be given as the input to the valve control system. Here the output of the machine learning will be an either 0 or 1, that is whether we have to open the valve or close the valve based on the prediction by using the collected data, and this output is given as the input to the valve control system. Valve control system consists of a solenoid valve and which can be connected by using a relay. By using the relay we can either open or close the valve, and here the requirement of water is checked again and again each for every 10 minutes. That is, for our 10 minutes delay we can open the valve or close the valve. For every 10 minutes the machine learning algorithm will get resets, and it will again predicts based on the real time value, not with the previous value. For 10 minutes once it will get updated. And finally, communication infrastructure. For connected with the cloud for computing and storage purposes for historical trends in our previous steps. So communication infrastructure such as IoT devices to connect the sensors which are deployed in the field, and as well as our AI system as well as our valve control system. We are using the IoT devices, and this allows for the real-time data transmissions, not relying on the database or any previous data. It will be real-time monitoring system. And this is our technology stack. That is, as I already mentioned, we are using the sensors, TDR sensor and DHT sensors. And Raspberry Pi is for collecting all these data collections, and for predicting that is for machine learning purpose and predictive analysis, we are using Raspberry Pi, and this is connected with the cloud for connecting the user interface. And then machine learning and deep learning algorithm, that is in our AI system, to determine the deep learning is to determine the plant type, growth stage and soil type, and machine learning is to identify the whether we have to open or close the valve. And finally servo motor to regulate the valve, solenoid valve. And this is our flowchart model. That is, in the field we are first deploying the sensors. From these sensors we are getting soil moisture levels and temperature and humidity level, and then followed by in the field we are also placing camera modules, and from this camera we can capture plant image as well as the soil image. There are many types of plants. It can be anything, and plant image and soil image such as to determine the soil type. We have different types of soil such as alluvial soil and some other soils. And then deep learning algorithms, and deep learning algorithms is determine the type of the plant, growth stage and as well as also the soil type. And all these 4 parameters are given as the input for one side, and these parameters are compared with the field capacity data set which are given as trained. We trained our model using that field capacity model, and it will determine based on the weather conditions, plant type, growth stage and soil type and available soil moisture level, and based on these values our machine learning algorithm will predict and decide whether we have to open the valve or close the valve. And this is our flow of work model, and then this is our workflow diagram. Here I have taken sunflower field as the input. Sunflower field, consider the example of sunflower field. Here we are taking single sunflower plant for prototype model. Here we are placing the camera module. This camera module will capture the plant, this image of the plant as well as the image of the soil type. This is given to our AI system. Our AI system will determine the plant type, growth stage as well as the soil type. And parallelly we are placing also TDR sensors, DHT sensors to determine the soil moisture level as well as weather forecast. And all these inputs are given as input to the processor. In our case we are using Raspberry Pi, and all these inputs are given as input to the processor, and our processor using machine learning predictive analysis will determine whether we have to open the valve or close the valve, and our algorithm will determine the fast and smart decision making as well. Also here servo motor is to control our solenoid valve, and user friendly interface is to connect to the farmers, to connect our AI system to the farmers so that farmer can monitor the status of our system. here whether he can manually control the valve, or else he can allow our AI system to control the valve in case of any emergencies occurs. And here this is use cases and dependencies. Use cases, it our advanced AI precision algorithm to automatically adjust the walls. And a water conservation, this is our main motto, that is to reduce the water wastage and to increase the yield optimization. And in crop health and yield optimization, and we can maximize the yields, that's the concept here. And then user friendly interface, farmer can monitor the status of the user friendly interface can be either a web application or the mobile application. And system alert system is to notify the farmers either through a message or through notification to inform the farmer if any exceptional cases occurs, that is excessive dryness or potential water wastage that occurs. It will be immediately notified to the farmers. And then cost reduction, it reduces the labor and operational costs in manual irrigation system. In smart irrigation system, actually a person will be there. So in traditional irrigation system, a manual person will be there to flow the water into the field. And then comes the concept of smart irrigation system. In smart irrigation system, there will be no person involved, but they are connected using IoT devices. They are flowing the water based on the schedule based, that is half an hour once or 1 hour once the water will get flowed. And there is a disadvantages is that whether the crop required water or not, the flow water will get flowed based on the schedule. So here our concept is precision irrigation, that is it will bridge the gap between the crop and as well as the water flow irrigation, that is if whether the plant required or not, based on that the flow of water will get occurred. If the plant does not require water, it will not flow the water. If the plant requires water, it will flow the water. So it bridges the gap between the crop requirements as well as the water flow regulation. And these are the dependencies as integration with the existing irrigation infrastructure. Our model can be integrated with the existing irrigation system, whether the irrigation may be drip irrigation or micropiped irrigation. Our system can be deployed in the valve of the existing irrigation infrastructure as well as the real-time remote monitoring. For example, the sensors which are placed will be continuously monitoring the data and it will be continuously sent to the processor, so that we are relying on the real-time remote monitoring, and it will get updated for every 10 minutes. And scalable and modular designs, and we can adapt our algorithm to the scale. It can be scaled up to a large size of fields. And comprehensive support ecosystem, and providing training and support to the farmer for system adoption is one of the dependencies, that the user friendly interface can be made farmers to easily understand our system and how it works, and the flow of the work we can be easily understood by the farmers. And this is our idea solution. We expect that we can easily provide this prototype, and it will be an effective algorithm, so that we can reduce the water wastage as well as we can increase the crop yield optimization. And coming to the cost wise, when compared to the other systems, our model system will be with less cost, and as well as also when compared with the yield, that is more growth and yield will be increased. So when compared with the cost of our system, that is farmer will get happy. And then these are about our project idea, and this is our team details. And we are from final year, and Varsha is from second year, and our team mentor one is Dr. S. Muthumanikam sir, was a domain experience of more than 20 years. He is from an academic category. And the industry mentor is Mr. Kiran R, and his expertise in application development and his domain experience of more than 5 years. And thank you so much for your patient listening. Thank you so much.